Good morning, ladies and gentlemen. I'd like to welcome you to today's webinar, Industrial Explosion Protection for Biomass Facilities, sponsored by IEP Technologies. I am your moderator, Anna Sinnott, editor of Biomass magazine. Our lineup of speakers today include Martin Cloutier of Jensen Hughes, Mika Vanis of Addix and Oy, and Dave Granda of IEP Technologies. Before we begin, just a few housekeeping items. Following completion of our last presentation, there will be a Q&A session as time allows. If you have a question for all of our panelists or just one, you can submit them at any time. You can specify who the question is for if you'd like. Questions not answered during the webinar will be forwarded on to our panelists who may answer them after the webinar as time allows. A free recording of the webinar will be available within a couple of days following. It can be accessed on the Biomass magazine website under the Events tab. The slides will not be available. You can contact presenters directly to get copies of those. Moving along to a quick overview of today's webinar. Our speakers, they'll discuss principles of combustible dust explosions, primary and secondary explosions, hazard assessment and ignition risks, spark detection and suppression, explosion protection strategies, and finally, process vessels at risk. And that about covers it. So I'm going to turn it over to our first speaker, Martin Cloutier of Jensen Hughes. Martin, go right ahead.
Thank you very much, Anna. It's a pleasure to be here. This is actually the second occasion I've had the opportunity to present at this annual webinar. I've also looked at previous year's webinars, and today I'm going to try to supplement the information that has been previously provided, because as you pointed out, these webinars are available for viewing. I'd like to first start very quickly with the basics, point you also to some resources along with teaser information about dust explosion incidents. I'll also use most of my time actually to talk about DHAs. In terms of DHAs, I'd like to touch on why they're required, talk about standards that are used in North America to support the performance of a dust hazard analysis, and talk about the main components and specifically technical aspects of each key step of performing a DHA. Those dealing with the confusing array of different types of tests that you can perform to characterize material hazards, talk about the approach to equipment hazard evaluations, and also, most importantly, how to prevent major accidents and multiple fatalities. I'm going to start with, bear with me, some very basic geometry to show the concepts that differentiate between fire, dust, flash fire, and dust explosion hazards. I'm sure that everyone is familiar with the fire triangle and the components that are necessary to produce a fire. If you've ever taken a significant amount of flour and thrown it on a campfire, I think that you would have a good indication of what constitutes a flash fire. There's four basic components in addition to that you would require one addition to the fire triangle. Basically, you need to have the dust that's mixed in air. If you're going to produce a dust explosion, you need a fifth component, and that's confinement. As I'll talk about later in this webinar, it doesn't need to be a complete total confinement. It can actually be partial confinement. And I'll talk about how those conditions arise and what actually results in equipment explosions and dust explosions. This is a list of what you might call the usual suspects where dust explosions are known to occur in terms of equipment hazards. Unfortunately, as operators of biomass producing or biomass handling facilities, you will readily recognize all of these equipment as being ubiquitous in your industry. I will talk about how these equipment become involved in dust deflagrations or dust explosions in more detail later in this webinar. I don't want to take up a lot of time, since any search on the internet will readily show you so many examples of dust explosions that have happened in industry. In the media, it's easy to find these examples. Unfortunately, as a safety practitioner, it's often frustrating because they're extremely lacking in detail. These are two well-known incidents that occurred, one most recently in 2017 involving a conveyor fire that resulted in extensive damage in Port Arthur. I'd like to invite you to explore an annual publication that talks about various incidents related to combustible dust fires and explosions, and they talk about, for example, one recent incident in Canada in December of 2017. This was a newly converted boiler firing on biomass pellets. So if the URL to retrieve that more information on that incident is available at the bottom. This is an overview of the combustible dust incidents which occurred in 2017. You'll see that in North America, compared to the international data, there seems to be an increased amount of incidents. The bad news, I think, is that generally speaking, you cannot say that the trend of dust explosions, dust flash fire, and dust fire incidents is decreasing. This shows the incidents as they progressed over 2017. The key takeaway, I think, is that despite a large amount of normative engineering standards that provide technical guidelines on preventing and mitigating dust explosions, these incidents seem to occur regularly in North America. So what's transpired in industry to address these trends? What have stakeholders done? And probably most importantly in your mind is, what can facility operators do now? It's a long story, but it's sufficient to say that there is a straightforward answer, and that is to engage someone who is qualified, a subject matter expert, to perform what's called a dust hazard analysis, or a DHA. Not only will this help you save lives and reduce operational and reputational risk, but it will also help you save money by screening out non-credible hazards and helping to prioritize capital spending. Interestingly, we should all be aware and know that there is a mandatory retroactive requirement in all of the occupancy-specific NFPA standards. These are not code, but they're frequently adopted by code, and therefore they do become regulatory requirements. The NFPA standards actually represent what you could call good engineering practice, primarily in North America, but these standards are also used internationally and Canada. This graphic shows the hierarchical relationship among the various primary standards that are mainly applicable to combustible dust occupancies. The NFPA 652 document is pretty much the umbrella standard, which provides fundamentals of combustible dust and hazards. It also points you to different test methodologies and the occupancy specific standards, which can be used to identify hazards at facilities and in specific equipment. There are design methodologies such as NFPA 68 and 69. 68 deals with the design of explosion protection by deflagration venting, and NFPA 69 deals with explosion prevention. The National Electrical Code, NFPA 70, also points to 77, which deals with electrostatic hazards. NFPA 49 helps you determine and delineate the extent to which hazardous areas should be established for classified electrical equipment. These are specific excerpts from 3 NFPA standards that relate to the requirements for that relate to the biomass handling and producing industry, and they basically show the requirement for a DHA and the relevant chapters and sections that talk about that. NFPA 652 in the annex material will actually give you an example of what constitutes an acceptable and defensible dust hazard analysis, or DHA. This is a more specific graphic to biomass handling. Basically, whether it's wood pallets, you would use the occupancy specific standard NFPA 664, and if it's an agricultural biomass, NFPA 61 is the governing standard. Once you've identified hazards and you intend to mitigate or prevent deflagration or explosion hazards, you would use more specific documents such as NFPA 669, 68, 499, or 654. 654 is a catch-all document that applies to dust-producing facilities where there are deflagration hazards, but they're not caught in either NFPA 664 or 484 or some of the other occupancy-specific standards. So what is a DHA? Basically, the objectives are straightforward. There's 3. You want to identify credible deflagration hazards, credible explosion hazards, credible fire hazards. The next objective is to identify, if it's an existing facility, what, if any, are the gaps between what is considered good engineering practice, exemplified by the NFPA standards, and existing conditions. If it's a proposed facility, you want to identify gaps between the proposed basis for safety, the proposed safeguards that you're endeavoring to provide for your plant, and good engineering practice. The third objective is to offer practicable recommendations to address those gaps. There are 3 main components to a DHA. The first component is to characterize the material hazards, and I'll talk about that. I'll talk about each part separately further in this presentation. The second part of a DHA is to evaluate equipment hazards, basically to identify credible explosion hazards in equipment. And then finally, the most important part is arguably to ascertain whether or not you have building flash fire explosion hazards. There are 3 types of DHAs. I have a very brief amount of time available for this presentation, so I'll just quickly say that prescriptive approach to DHAs basically involves looking at what's recommended prescriptively in the applicable NFPA standards and then offering recommendations to address gaps. Performance-based approach to performing a DHA and providing a defensible basis for safety is to show if you have a different design that doesn't necessarily meet the prescriptive standards but addresses the objectives and the goals of the prescriptive requirements. If you can demonstrate that you meet those requirements, then that would be a performance-based approach. Finally, a risk analysis approach examines the potential consequences and likelihood of an incident or a deflagration involving, for example, a specific piece of equipment. If the risks are determined to be acceptable, then you can demonstrate that you have, without necessarily following the prescriptive standards, a defensible basis for safety. I'm now going to talk about the first part, which is a material hazard analysis. There are numerous parameters that influence the reactivity of a material, or the explosibility or the ignition sensitivity, if you will. There are the physical and chemical properties of the dust, there's of the oxidant, and also there's factors such as how the dust is dispersed, the turbulence involved, flow conditions, the geometry. High length to diameter ratios of certain pieces of equipment can exacerbate a deflagration and make it cause greater overpressures and much more violent deflagrations that require more rigorous explosion protection or prevention measures. Ignition, the strength of ignition source can also influence the outcome or the consequences of a deflagration. So in performing a DHA, it's important to characterize the material hazards. I think one of the most important takeaways from the understanding the factors that can influence the explosibility of material, by far the most important parameter, the dominant influence on explosibility of material is the particle size. The smaller the particles, the more violently they will explode. So the one very important takeaway is that these are not fundamental properties. They actually vary depending on what facility you're evaluating, what process, where in the process the material is located. It's very, very important to actually test the material that you are evaluating. These are different explosibility parameters that are commonly used throughout the world to evaluate the potential violence of a dust explosion and also how sensitive the material is to ignition. Pmax and KST. KST is a term, a volume normalized maximum rate of pressure rise in a constant volume deflagration. This concept was developed in Germany, so it's not surprising that ST stands for Staub, which is German for dust. Pmax and KST are two parameters that are used both in the design of explosion suppression systems and deflagration venting. And there'll be more discussion about this later in this webinar. The other parameters, MEC, MIE, and so on, they characterize how sensitive a material is to ignition. For example, minimum explosible concentration will tell you how much material needs to be dispersed in the air to pose a credible deflagration or explosion hazard. The MIE is the minimum ignition energy. There are a few ways, there's a couple of different ways to measure that, either with or without inductance. We don't have time to talk about that, but it's an important question to ask before you start testing. So this is just a slide that shows the general hazard classification scheme that was originally developed by Barknecht. The hazard class is ST1, 2, or 3. By far, almost, I would say, all biomass materials have KSDs less than 200 bar meters per second. Just for comparison, you can see some example values for wood dust, forestry waste, and sewage sludge. These, again, should not be used for designing explosion protection or suppression systems or to characterize ignition sensitivity, because I'd like to emphasize that these parameters are not fundamental properties. This is taken from a publication by the Transportation and Feeding, i.e. Bioenergy. It shows values, various explosion severity and ignition sensitivity parameters for pine dust, bark dust, and compares them to coal dust. As you can see, perhaps surprisingly, biomass dust can be as or more hazardous in terms of explosion violence and ignition sensitivity compared to coal dust. These are two apparatus that are commonly used to characterize, to determine KST and Pmax, and also minimum explosible concentration. These equipment are also used sometimes to determine minimum ignition energy. By and large, biomass dust has an MIE that is very low, and these equipment, more sensitive equipment, are used to determine what the ignition sensitivity of that material is. The gold standard in the world for truly determining the explosion severity of a dust at industrial scale is the cubic meter chamber. However, there's an enormous amount of material that's required and resources and expense to test in a cubic meter chamber. For this reason, many years ago, a smaller bench scale apparatus, commonly called the 20-liter sphere or the 20-liter CVEC chamber, was developed to show, to basically calibrate it to give similar results to what can be achieved in the cubic meter chamber. However, if you truly want to know your hazards and you have enough material and resources to determine the explosibility parameters in a cubic meter, it's a good idea to do that. This is just a graphic showing a comparison of numerous values that were determined for various dusts, comparing the KST values for the determined in the cubic meter chamber and comparing it to the 20-liter chamber. Although this shows a perhaps rosy outlook on the perfect correlation between the 20-liter and the cubic meter, this is not true in reality. There are many different types of dust that actually don't correlate well in both vessels. And there are many occasions when you want to actually test in the cubic meter to be sure that you have good understanding of your hazards. The 20-liter chamber, this is just a schematic showing the layout. Basically, a vacuum is pulled, the dust is dispersed, and there are chemical igniters that are used to ignite the dispersed dust cloud. The rate of pressure is measured as it increases, as well as the maximum pressure. This is a comparison of basic operating parameters for the cubic meter and the 20-liter chamber. Just for comparison, OSHA often uses an apparatus called the U.S. Bureau of Mines 20-liter chamber. That is actually not well suited for determining KST and Pmax because the turbulence is much lower and the KST and Pmax values would be lower than you would obtain in the cubic meter 20-liter chamber. However, this apparatus is commonly used to evaluate whether or not a material is explosible. The takeaway from this slide is that the U.S. Bureau of Mines 20-liter apparatus actually has less conservative operating parameters. So if a material or a dust is determined to be explosible in the 20-liter, then it is most certainly explosible in the 20-liter CVEC chamber or the cubic meter chamber. Now to shift to equipment hazards. These are common equipment found in the biomass producing and handling industry. They are all known to have been victims or instigators in dust explosion incidents. This is a compilation of incident data that can be found in the CCPS guideline for safe handling of powder and bulk solids. It gives you an indication of the relative frequency of various types of equipment. By far in North America, approximately, well, the most dust explosions in industry involve dust collectors. one of the reasons for this is it is highly conducive to producing all of the 5 conditions that are necessary to produce a dust explosion. You have material that is flowing through ductwork that accumulates electrostatic charge, and normally dust collectors require filters that are pulsed. At that time, the dust is dispersed, usually above the minimum exposable concentration. The jostling can cause the filter cages and the tube sheet to discharge an incendiary electrostatic discharge, which can ignite the dust cloud. So it's not surprising that at least half of the dust explosions in North America involve dust collectors. So this table gives you an idea of how you might want to prioritize allocation of capital expenditure to address explosion hazards at your facility. There is one thing that safety practitioners will tell you about process safety, and that is that ignition sources are the only thing that's free. This is a just brief list of the common ignition sources that are known to have caused dust fires, deflagrations, and explosions. It gives you an indication of how many different types of ignition sources there are, and also the range of ignition source strength that is available. Open flames and hot work are very strong ignition sources, but actually, as I'll talk about in the next slide, there are most biomass materials, if the particle size is small enough, are susceptible to very small ignition by very small energies that are commensurate with electrostatic discharge. This is a graphic from NFPA 77. It shows the various types of electrostatic discharge which can occur as a result of triboelectric charge accumulation. Corona brush, bulking brush, propagating brush, and spark energies are all usually can be demonstrated to be sufficiently strong to ignite biomass materials. The last, but arguably the most important part of a DHA is to evaluate whether or not there is potential for a flash fire or explosion in the building. Although it's arguably the most important part of a DHA, it's the simplest to address and the simplest to identify. If you walk through your facility and you cannot discern the surface color underneath a layer of dust, or if you can write your name in the dust, this is a strong indication that further evaluations are needed to characterize whether that fugitive dust accumulation is hazardous and poses a flash fire or explosion hazard. The bottom line, and probably the most important thing that you could do at your facility to prevent major accidents and to prevent multiple fatalities, is to implement rigorous housekeeping procedures at your facility, at elevated surfaces, at the joists and the rafters of your facility, throughout the facility. If you can eliminate hazardous fugitive dust accumulation, you've taken extraordinary steps towards preventing a major accident or multiple fatalities. I think that's it for me. I've run out of time, but thank you for the opportunity. I look forward to any questions that you might have.
Thank you, Martin. Great job at getting things started. We'll just move right along. Next up on the panel is Mika Vanis of Addicts and Oi. Welcome, Mika. Thanks for joining us today.
Thank you, Martin and Anna. And hello, everybody online. I'm going to present now how spark detection and extinguishing systems can be used to suppress ignition sources in biomass industry. We will go through the most typical ignition sources, consequences that can happen if ignition sources travels in conveying lines, and we will also go through some important system parameters for spark detection with biomass applications. It is known that there are 14 different or 13 different ignition sources that can ignite dust explosion. Martin had a longer list in his presentation, but I am concentrating here to 4 of them, which are the most interested in spark detection and extinguishing point of view. The first, mechanical failure, is a very common cause of fire or explosion accident. Mechanical movement greater than 1 meter per second can produce mechanical sparks or spark streams. Typical example is ball bearing failure of dust extraction fan, especially if the fan is located at dirty side of the dust collector. Friction heat generation is also a big problem because it can produce hot particles or even embers that contain a lot of energy for igniting dust explosion. Typical example is stalled conveyor roller. Impurities in the processed material flow are dangerous too, because they can enter into hammer mill or other high-speed machine. All impurities cannot be separated with magnetic separators, and there are also cases that magnetic separators have failed. And the last one, self-ignition, is the most difficult to understand because there are many factors affecting this phenomenon. For example, high humidity level or freshness of a biomass fuel leads to bigger risk of self-ignition. But the good thing is that this can be detected with multi-criteria gas detectors integrated to spark detection and extinguishing systems. Here we have some typical consequences listed what can happen if ignition sources are not suppressed from production lines. Dust explosion is of course the most dangerous one because it can cause huge damages to production lines, facilities, and also to workers. The purpose of spark detection and extinguishing system is to suppress ignition sources before they enter in the dust explosive area. It is not always dust explosion that can happen, but many times just local fire in certain area of the production line. And even though smaller local fires cause many times relatively long production stops. And the last but not least, life safety threat is something that can be never underestimated. At least 900 workers have been killed or injured in dust fires or explosions since 1980. It is a common question, how can a spark be detected? Sparks and hot particles, like embers, they radiate an electromagnetic radiation. Spark detector is very sensitive for this radiation, even through some dust layers. Very special electronics and optics are needed because sensitivity level and response time have to be in so high level. There are also challenges like very high material flow speed or high process temperature, which can radiate many times stronger signal than a small spark. Spark detectors are sensitive to wide range of radiation from visible light to infrared range. Here we have a description how entire spark detection and extinguishing system works in dust extraction system. You can see those yellow ignition sources or sparks traveling to dust collector. Oppositely installed spark detectors, number 1, react to sparks and send signal to system control unit, which then activates water extinguishing, number 2. Water is sprayed from nozzles into dust pipe, typically only for 5 seconds after last spark. The fan controller, number 6, stops the fan in case of fan overheating or sparks over. Typical limit for sparks over is 3 sparks within 6 seconds. The function of pressure booster station numbers 8 and 9 is to provide airless extinguishing water with sufficient water pressure level that optimized water droplet size and extinguishing response time can be achieved. Pressure booster controller also takes care of pipe and extinguisher heating in case of outdoor installation. This slide describes how to protect a chute between 2 conveyors. And basically, everything is the same to dust pipe protection. The most important difference is significantly lower material speed, which leads to shorter distance between spark detection and extinguishing points. Typical distance with dust pipe is something like 6 to 7 meters, but with chutes, the distance is typically only 1 to 2 meters. The other differences are number of needed detectors and water nozzles, because protection area is typically bigger with chutes and material flow is more dense. This slide describes how to protect a chute handling biomass that cannot tolerate water. In the left picture, we have a bucket elevator which transports grain dust from silo to burner. On the right picture, we see a diverter which diverts the material flow to left branch, which goes to blue fine screener. So this is the normal direction of material flow. During the alarm, when spark is detected, spark detection system control the diverter and guides the material flow and ignition sources to waste gate. This way we don't need to spray water into fine screener that could lead to mess or even porridge, because the powder is now grain dust. After 5 seconds, spark detection system deactivates water spray and diverter will return to normal mode. And pressure booster station, which contains water pump and tanks, is similar to dust pipe protection. Biomass processes set new requirements for spark detection. Conventional spark detectors, which are especially designed for low-dense material flow, have limited viewing angle or field of view. Picture 1 describes that a detector having 110-degree viewing angle works without any problems with dust extraction pipes, because opposite detector covers blind spots of the other detector. Picture 2 shows that what will happen if the same detector is used for biomass applications having dense material flow. The opposite detector cannot anymore cover blind spots of the other detector, and risk for unrecognized ignition sources are significantly increased. Picture 3 shows that spark detector, which has 180-degree viewing angle, needs to measure only half distance because the other detector takes care of the other half. And this leads to 4 times better sensitivity level because of square law of radiation. And picture 4 shows how much better 180-degree detector works in biomass chute. Both detectors are needed to cover only half of the chute, and there is no need to see through thick material flow to cover blind spots of opposite detector. Another important need what biomass industry sets to spark detectors is detection spectrum. Hot particles are very important to be detected because biomass applications have a lot of reasons of producing them, and they can easily ignite fire or dust explosion. However, hot particles having temperature less than 550 Celsius degree do not emit any daylight. For that reason, infrared detection is needed. A drawback of infrared radiation is that water absorbs it and biomass always contains some moisture. We also know that if we are using portable or handheld infrared temperature meter, we are always measuring the surface, but not what is behind the wall or surface. At the same time, if we use a detector which is sensitive only visible or near infrared area, some ignition sources like hot particles cannot be detected. The best choice for biomass application is broad spectrum spark detectors that can measure all radiation which doesn't belong to protection area. That kind of detectors can measure visible light, near infrared light, and also infrared light. In the other words, it can measure hot particles, embers, flames, sparks, and many of them even through some material layers. But it's good to know that there are also applications like open conveyors that may require daylight filtering, and then visible light has to be filtered from the spark detector. But typically, spark detection targets are dark and enclosed areas like enclosed conveyors, dust pipes, or disc screens, where daylight filtering would cause only lack of information or radiation. This means that it's very important to choose correct type of detector for each application. Now we are going to go through key components of spark detection system. The first one is spark detector, which is the most important one, because if this small device fails or is not capable of detecting ignition sources, then the rest of the system is useless. Typical parameters for spark detectors are listed here, and they are an ability to detect various range of ignition sources like sparks and hot particles. Typical reaction time is only 1 millisecond. They are very rapid. High temperature versions are also available for dryers and ovens. And from daylight filtering possibilities and viewing angle properties we already discussed during previous slides. The second key component is spark extinguishing unit. This rapid extinguisher can produce full coverage water spray in the protection area within 50 to 100 milliseconds, depending on different application. Typical amount of extinguishing water is something like 5 liters for dust extraction pipes and 20 to 30 liters to conveyor chutes. There are available electrical ball valve monitoring systems for accidental valve closing that it can be monitored. Water flow sensor is very important for each protection area to localize possible water leaking or lack of extinguishing water during an alarm. Real-time temperature sensor helps monitoring aging and degradation of water pipe heating cables and also warns the user from poor insulation. There are also special type of nozzles, water nozzles, for different applications. For example, biomass applications typically need strong high flow nozzles. And then also dedicated insulation jackets are available for easy outdoor installations. And those jackets, they are lightweight, UV resistant, watertight, very easy to open and proceed maintenance for extinguisher when needed. Third key component is control panel, which is user interface for entire system. It has line monitoring for cables and devices. There are automatic battery backup function for detection and extinguishing. There are event log for later analysis that contains, for example, alarms, failures, proceeded tests, etc. Control panel communicates with factory process automation system. The control panel can be used also to disconnect protection zones during service, and it can forward also alarms to higher level fire prevention systems. Then there are additional detection consideration. Those last 3 slides, we tell a little bit more about those additional detection considerations. They are important part of fire prevention in biomass industry. Advanced spark detection system supports also other type of detectors, and now we will go through the most typical ones what we use. The first one is overheat detector, which is used for detecting, for example, ball bearing failure of dust extraction fan. It is known that about 50% of fire accidents in woodworking industry is ignited by overheated machine. It is important to measure temperature from long distance. For example, dust pipe blockage can be measured from perimeter of the fan, and ball bearing failure on the sidewall of the fan. Overheat detection is economic solution if the spark detection system support this function as a standard, and no external units are needed. It can increase safety level significantly and also provide preventative maintenance, because ball bearing failure is detected when temperature is only 100 Celsius degree, thus not being able to cause bigger damage to machine until the machine is stopped. Second additional detection consideration is a flame detector. This is applicable for example receiving stations and other open area monitoring. Also very good for machine monitoring. Reaction time is significantly longer to spark detectors, but still many times faster than smoke detectors. And typical reaction time is something like 3 seconds. Longer reaction time increase false alarm immunity, because the device has time for more complex analysis. Flame detector, which is connected to spark detection system, can control also water mist extinguishers for limited area or machine protection. In the photo, we can see flame detectors that are triggered water mist cube around the dust burner. And the last additional detection consideration is gas detectors. They are used to monitor fuel storages like silos to detect smoldering fires. And this is only monitoring because due to high silo volume, it's not possible to use conventional water extinguishing system to suppress silo fires. Water may also cause excessive expansion for biomass, and therefore water is not typically used. And local fire department can release inert gas or foam in the silo when needed. Okay, that was my presentation from spark detection and extinguishing systems in biomass industry. Thank you.
Thank you, Mika. Well done. Before we move on, let's hear a quick word from our sponsor.
IP Technologies, the name to trust for industrial explosion protection. IP Technologies is the worldwide leading provider of industrial explosion protection systems and services. For over 60 years, we have provided protection solutions that can suppress, isolate, and vent combustible dust or vapor explosions in process industries. IP Technologies can support biomass and ethanol operations through our facilities throughout the world, including in the US, Brazil, UK, Germany, Switzerland, France, Turkey, and China, designing and servicing systems with a dedicated team of application engineers, regional sales managers, and field engineers. The IEP Technologies process precise protection for every application. IEP Technologies has more worldwide experience protecting a wider range of facilities against explosions than any other company. With well over 15,000 systems installed, we have developed a unique process to ensure the highest level of protection for your facility. The IEP Technologies process includes material testing, an engineering site visit, system design, installation, commissioning, and maintenance. IEP Technologies also offers on-site training programs for the proper operation and understanding of your explosion protection system. IEP Technologies is a member of the Herberger System Solutions business segment, which provides comprehensive industrial safety solutions across a wide range of industries. Saving lives through explosion prevention and protection is the role of the IEP Technologies and Newson Gale brands at Herberger. IEP Technologies is the systems and service specialist for the entire range of explosion protection solutions in dust and gas applications, which now includes at a Texon range of spark detection and extinguishing solutions. Newson Gale brings decades of experience in mitigating fire and explosion risks from electrostatic spark discharges. These brands complement the flameless venting expertise that Herberger has accumulated over the decades, as well as their expertise in industrial engine and generator protection. You can't afford to let an explosion threaten your critical facility. Let us work with you to keep an explosion from impacting your bottom line. Call IEP Technologies today.
All right, thank you, IEP. Again, if you have a question, you can type it into the question box at any time. We will answer some of them during the Q&A following Dave's presentation. Unanswered questions will be sent to our panelists to follow up with you on. So let's just move right along. Our final presentation of this webinar will be given by Dave Granda of IEP Technologies. Dave, I'm going to turn it over to you.
Very good. Thank you very much. Thanks, Anna. In the previous two sections, we discussed how explosions initiate, how they propagate. We talked about some of the explosion prevention measures. And some of these measures are going to be employed on a weekly basis because there are just some malfunctions that just tend to happen in high velocity machines when you're moving a lot of product from point A to point B, when you're doing material particle size reduction and dust collection. For those instances, you certainly need the explosion prevention techniques built in to your overall plant safety strategy. There are unusual circumstances that occur which do result in actual explosions within vessels. And because of that, there are NFPA standards that do require the use of explosion protection systems of some sort. The standards that we're talking about specifically would be NFPA 654, which is for the manufacturing, processing, and handling of combustible particulate solids. NFPA 664, which is for wood processing. NFPA 652, which is basically a relatively new standard called the Fundamentals of Combustible Dust, which creates the foundation through which all of the other industry-specific standards are trying to strive to also invoke. Those standards basically tell you where explosion protection should be implemented. The two standards that tell you how those explosion protection measures need to be designed include NFPA 68, which covers deflagration vents, and NFPA 69, which is for explosion prevention systems. By far and away, the most common explosion protection method is explosion venting. Explosion vent is an opening in a process vessel through which combustion-generated gases can flow and expand. And the whole purpose for an explosion vent is to minimize the pressures that are developed during an explosion to a level below that at which you're going to have rupture or deformation to that vessel. Now, explosion vents come in quite a manner of different sizes and styles and shapes. Some are rupture style vents. There are other types of vents that may be held on with frangible bolts. Some are spring loaded, some are magnetic latches. Vents can be flat, some can be domed, especially in high pressure cycling applications. Dome vents tend to have a much longer service life. Vents can be round, square, rectangular. Some vents can come with sensors to provide a signal that should you have an incident that's causing the vents to open up, you get a signal that would indicate that this incident is happening, and you can stop the process so that if there is any combustion going on, you stop the promulgation of burning embers or sparks or fires to other parts of the process. Since explosion venting is generally the least expensive means of protecting a vessel, and therefore it's always preferred when possible, when can explosion vents be used? We need to remember that when an explosion vent is being used, you are releasing a very large fireball to the outside in a controlled manner through a specific opening within the process. Oftentimes, that vent will relieve a fireball that could be 7 to 8 times the volume of the vessel. And it doesn't come out in a nice round sphere. It comes out in a flame jet that can eject for 50 feet or more. I remember doing a recent vent calculation in which the vent flame ejection distance was 134 feet. So you could see a very, very long flame ejection distance. So it's very, very important when you're trying to determine whether or not explosion venting is a suitable protection option for your facility is, do I have a clean path for that flame to be ejected where you're not going to have people, you're not going to have a sidewalk, you're not going to have other parts of the building that could become ignited, other process vessels and so forth. So it's very, very critical that that be considered when determining if explosion venting is the right explosion protection technique for your application. This is a pressure time curve for explosion venting. A couple of things to keep in mind on this. The whole purpose for the explosion vent is to make sure that we keep the reduced pressure after venting below the vessel strength so that we don't see rupture or deformation of that vessel. The other thing I'd like you to take away from this particular graph is there's two separate values specific to the vent. And the first is P-stat. P-stat is the opening pressure for the explosion vent. The P-stat is always going to be lower than what the reduced pressure after venting, or P-red, ends up being calculated to. Meaning if you have an explosion vent that you've purchased with your vessel that is rated for opening at 1.5 psi, you cannot have a vessel that's rated for 1.5 psi, because the P-red is always going to be higher than P-stat, because there is a finite time between the opening of that vent and the point at which you're going to get the full effects of that pressure relief. So please keep that in mind, that you must keep the P-red below the vessel strength, and the P-stat is always going to be less than the P-red. NFPA 68 is the standard that we use here in primarily throughout North America for sizing of explosion vents. NFPA does allow the use of vent ducting to the outside if you have an inside vessel. So if you have a vessel that's near an outside wall, you can indeed put an explosion vent on that vessel and duct it to the outside. This is one thing that you can't do. The vent example we see in this photograph basically has some shear bolts on it. It's tethered. Unfortunately, it's also directed into the middle of the facility. So if you have wood dust from the processing on horizontal surfaces and this vent were to release, you would be ejecting a flame and a pressure shock wave into that room that would liberate that dust on the horizontal surfaces, causing secondary explosions. You'd probably blow up the room. So it's very, very critical that if you do have an inside vessel, that that vent, if you're going to put a vent on it, has to be ducted to the outside. And you also have to follow the NFPA calculations to determine what the overpressure effects are of having that vent duct. By placing a vent duct that's longer than the hydraulic diameter of that duct, of the vent opening, if that vent duct is longer than the hydraulic diameter of that opening, you're going to see back pressure. And the longer the vent duct is, the more the back pressure is going to be, which means that you're either going to have to oversize the vent to accommodate for that back pressure, or you're going to have to beef up the vessel to compensate for that back pressure. Another thing to keep in mind, explosion vents relieve pressure from the primary vessel. Explosion vents do not stop flame propagation from that vessel to interconnected vessels through ducts, pipes, chutes, and so forth. We'll cover that in a few minutes. In some instances, a different type of explosion vent can be used for inside applications where vent ducting is not practical, cannot be done safely to the outside, or the vent duct length is just too long to be suitable for the application. That would be the use of flameless vents. Flameless vents, there's two basic styles of flameless vents. There's a rupture panel style flameless vent, and then there's a spring-loaded style flameless vent with a plate that moves at a certain pressure. Both styles have basically a flame arrestor around the outside of them, so that when the overpressure from the explosion causes the vent to open up, the heat from the flame is absorbed as a heat sink through the flame arrestor, and then all that's ejected is hot gases. Those hot gases are basically cooled to somewhere around 160 to 200 degrees F. And there's no flame that then is released into the room. Now, we do have to keep in mind that 160 to 200 degrees F will scald someone. So there is still a safe area requirement around the perimeter of these flameless explosion vents. Typically 2 to 3 meters, depends on the type of vent it is, depends on the application, even depends on the distance. But oftentimes flameless vents are a good alternative to regular vents with ducting. And here's just a graphic of showing a spring-loaded style flameless vent. The picture on the left-hand side, you'll see the vent in its closed position. When the pressure from the explosion occurs, it'll push the plate up that's beneath that funnel-shaped spring, and the spring will compress. The flame and the hot dust will be pushed towards the flame arrestor, which will then absorb that heat and safely just release that heat to the outside without any flame. So this is just one alternative to standard explosion vents. Explosion suppression systems are another alternative to be considered. Explosion suppression systems work on the principle that during an explosion, you have a pressure that's growing at a basically sonic speeds, something approaching 1,100 feet per second. At the same time, your flame speeds are somewhere in the vicinity of 3 to 10 meters per second initially. Now that speed will increase depending on geometry of the vessel and time. But initially, the flame speed is relatively slow in comparison to the pressure development rate. The explosion suppression systems take advantage of this gap between the pressure front and the flame front by detecting that pressure very, very quickly, suppressing the fireball. And typically, from the time an explosion begins, while it's being detected, the extinguishers discharge, and the suppression is completely finished, is something between 70 and 130 milliseconds, depending on the application. Here is a quick animation showing an explosion within a dust collector. We'll see an ignition source, the pressure that travels up, detected by the detector. Very, very quickly, flame is ejected, powder is ejected to absorb the heat from the flame. And in conjunction with that, you'll see an extinguisher on the inlet duct, and that extinguisher discharges to create a chemical barrier to stop any flame going back upstream. The main components from an explosion suppression system, very similar to a fire suppression methodology, in that you have detection, control, and extinguishers. The detectors are typically pressure-activated detectors that can either be static detectors that would look for a specific programmed or calibrated detection set point, or they could be rate of rise detectors that are looking for a specific rate of pressure increase that would be synonymous with an explosion from that hazard within that volume vessel. Control panels pick up the signal from the detectors. They signal the extinguishers to discharge. They also signal the process to shut down so that you stop any equipment that moves product or air through the protected volume. And then finally, the extinguishers are typically high pressure extinguishers that are filled with a sodium bicarbonate based dry chem. Extinguisher discharge velocity can be approaching 200 feet per second. So you get a very, very fast rate of agent discharge within the protected vessel to extinguish the deflagration in its very early stages. Number of parameters that are taken into account for an explosion suppression system, and that includes this material explosibility characteristics that Martin had discussed earlier, KST value, Pmax value, auto ignition temperature of the material. Those are all factors in determining an explosion suppression solution. The process conditions, what sort of operating pressure, sort of operating temperature, process location, vessel strength, vessel volume, vessel L over D. These are all parameters that have to be taken into account when designing an explosion suppression system. Explosion suppression systems are a bit different than fire suppression systems. Most fire suppression systems use a volume versus concentration design methodology. With explosion suppression, the science is quite a bit more advanced than that. There's a lot of things that can affect whether an explosion suppression system will work correctly and be able to put out an explosion within a given threat. Certainly how fast the explosion is going to grow within that vessel. Martin discussed earlier how a high L over D or length over diameter ratio vessel is going to have a much more intense explosion than something that's more of a box or a sphere. So that's taken into account. What pressure you have your detection set at will have an effect. Even the orientation of an extinguisher, whether you're discharging vertically or horizontally, will have an effect. The type of suppressant, the efficiency of the suppressant, how far you have to throw the agent. If you have to put an extinguisher, use an extinguisher to put out an explosion that's 3 or 4 feet away, is a different animal than if you have to put out an explosion that may be 12 or 16 feet throw for that extinguisher. So it's really important that explosion suppression systems take these parameters into account, and typically a computer model is used so that you can get an output to determine the efficacy of a system design. Regardless of whether you're using explosion venting, flameless explosion venting, or explosion suppression at a process vessel in a biomass facility, these vessels are fed from somewhere and typically discharged somewhere. If there's not an adequate mechanical barrier in between vessel A and vessel B, that flame can propagate. And the propagating explosion can create some very, very high ignition energy sources which would result in the secondary or the connected vessel having a much more dynamic explosion than the initial one if that explosion propagation is not caught. As a result of that, NFPA, in a number of different standards, have specific requirements for the use of explosion isolation. That means to stop that flame from traveling from one vessel to another. There's 2 basic categories of explosion isolation. One is have active explosion isolation, and the other is passive explosion isolation. An active explosion isolation system would be the one that we see in the upper right-hand corner. That would be a form of active. That would be a chemical barrier. The 2 lower ones, one is a flow-style actuated valve, the other is a flap-style valve. Those would be more of a passive type of isolation system, and we'll cover each of those next. The active type systems would typically consist of a detection method, a control panel, and either a chemical or a mechanical isolation barrier that's triggered by that control panel. The detection method can be either the pressure detectors that were shown during the explosion suppression slide, whether it be a static detector or a dynamic type detector, or that detection method could be an IR detector on the duct, detecting flame as it's traveling through, and then very, very quickly discharging extinguishers to create a chemical barrier to arrest that flame as it's traveling through the duct. The high-speed isolation valve that's shown on the left or the right 2 pictures, those are basically knife gate valves, orifice knife gate valves that are signaled to activate very quickly and to close within milliseconds to stop that flame from traveling through the duct. Mechanical isolation valves, such as those shown, will probably not be used within the biomass industry in most applications, both because of the strength of the duct that's necessary. You basically have to have pipe to install these isolation valves on, because you are bottling up the pressure from that explosion. And the cost. There's a very high cost for this style of isolation valve. So you would find this valve more suitable for applications such as pharmaceutical, where you have a very high valued product that you can't afford to contaminate with, say, a dry chemical powder. Passive isolation valves typically work on the pressure from the explosion itself, causing the valve to close. So remembering the principle that you have pressure traveling much faster than the flame front, that we take advantage of that principle in a passive explosion isolation valve. In this case, we're showing a flap style isolation valve where an explosion that happens from the vessel has pressure preceding it. This pressure is going to be traveling down the duct back toward the valve, and that pressure hits the flap. It causes the flap to close, creates a mechanical barrier. So basically, it's like a big check valve that's in the duct. Very simple process. Now, there are some NFPA 69 minimum prescriptive requirements for the design and implementation of these styles of valves. The first and maybe most important one is they do have to be third-party performance-based, tested and approved for the intended use as an explosion isolation device. So they have to be tested and approved as for use in explosive conditions to make sure that they are going to stop that flame. Make sure that they're strong enough to hold up to that pressure that's going to come back through the duct. These valves have become much more popular in recent years. One of the very important functions of these valves is that they have to be in a level or flat or horizontal type of a orientation in order for the valve to work properly. So this is something to consider when designing, say, a dust collection system for a biomass facility. You want to take advantage of this style of an isolation barrier. You want to make sure that when the duct routing is being designed, that you take into consideration that there's a certain minimum distance upstream in which this valve has to be placed before it can be before you can start branching out and doing your other pickup points. The different explosion protection techniques that we just discussed, there's a number of different things that you should be looked at when you're trying to determine which protection methodology would be best for your application. Certainly the explosivity characteristics of the material are very important. As Martin mentioned earlier, most dust that we'll find in a biomass facility is going to have a KST value of 200 or less. So it's an ST1 dust. One sidebar on that, between 85 and 90% of all combustible dust fall into that ST1 category. So please do not get caught in the trap of hearing that, oh, I just have an ST1 dust. It's not as severe as the others, so I don't have as much of a risk. That's really not the case at all. All that ST value tells us who design protection methods with the KST, using the KST value, is how much time do we have to react to an explosion? How much time, whether it's a KST 190 or a KST 90, that tells us how much time we have to react. As the end user, as you, the user, who's going to have this vessel that is equipped with this explosion protection method, whether this explosion happens in 200 milliseconds or 400 milliseconds won't matter to you. You're still going to have the explosion. It's still going to cause significant damage. So don't get caught in the trap of I don't have an explosion threat because I just have an ST1 dust. Location of vessel is going to have a big impact, obviously, to determine whether or not your vessel can be safely vented to the outside. The inlet duct configuration, that's going to help tell us whether or not a flap valve will work, or whether or not we need to use a chemical barrier to stop flame propagation. The exhaust duct. In some cases, especially in the northern climates, the exhaust from say, dust collectors is to go back into the facility for energy conservation. If that happens, then we have some other things to consider. The potential for there to be fire and or explosion propagation through that duct during a deflagration or a conflagration event. And that will have some effect on the type of protection needed. Certainly operating pressure has an effect. Even an inline fan, which can be an inline ignition source, will have some effect on the protection method that should be employed. Martin discussed a bit earlier about the explosivity characteristics. So I won't cover this too much, but these are very important characteristics to know when you're trying to determine, number one, do I have a risk of electrostatic ignition that could cause a spark somewhere within my biomass facility process flow that could cause a deflagration. That would be something that would be tested under the dust cloud minimum ignition energy testing. When you're doing drying, minimum dust cloud ignition temperatures, minimum dust layer ignition temperatures, those are important parameters to understand. And of course, we talked about the KST and the Pmax earlier. I do want to just quickly cover some of the more common explosion risks as far as processed vessels within a biomass facility. And far and away, the one that is more commonly involved in any other type of vessels is dust collector. In addition to the parameters that Martin had mentioned, the dust collector has the finest material within the entire plant. And if you think of that fine material as comparing it to a log versus kindling, the finer the dust, easier it is to ignite, meaning the least amount of ignition energy is necessary to start a deflagration. In addition, the finer the dust, the more severe the explosion properties are going to be. The faster the rate of pressure development is going to be, the higher the KST, the higher the Pmax, the easier it is to ignite. One other factor about dust collectors, if you have an explosion in a dust collector, oftentimes that dust collector is serving multiple vessels. So you're pulling dust from multiple sources. So a dust collector that has an explosion within it that travels upstream can affect multiple areas of the plant. So you can have multiple explosions within the facility if that explosion has not been isolated. Another type of vessel that's used at biomass facilities for separating particulate from the airstream would be cyclones. Cyclones basically have the same type of explosion risks that you would find in a dust collector. Cyclones are a bit more of a challenge for explosion venting since having a flat vent on a cylindrical vessel that's using tangential force to separate dust can mean some inefficiencies in your dust separation. But explosion venting can be used if put up above the vortex finder or up on the shoulder of the cyclone. Otherwise, explosion suppression would be probably the main explosion protection method that would be employed. Mills, fogs, pulverizers, one of the most common ignition threats that you'll find in a biomass facility. And as a result, the risk of at the mills is not just at the mill itself, but you might not have the right dust air mix for an explosion to occur in the mill itself, but as that product is being conveyed downstream to a receiving vessel, whether it's being conveyed by gravity into a hopper, whether it's being conveyed pneumatically to a receiver of some sort, that next interconnected vessel is also at real risk of seeing an explosion. So when you look at the threat around mills, you really want to look at the mill itself, where it's being fed from, any makeup air that may be used to pneumatically transport that product somewhere downstream, and then the next vessel downstream. Mechanical and pneumatic conveying are both explosion threats within biomass facilities. Hoppers and silos, Mika discussed earlier the potential for spontaneous ignition. You also can have hot burning material that's being transmitted from somewhere upstream that can get into hoppers and silos. The photo on the right is actually a biomass facility that was converted from a coal-fired plant to a biomass. And as you can see, those particular silos are equipped with explosion vents. Those vents have to be placed above whatever the upper product level is within the protected vessel, since vents aren't made to have product resting against them. We've covered quite a bit of material over the last hour, almost hour and a half now. Just kind of as a brief summary of what we talked about. When you're trying to determine your explosion threats at a biomass facility, it's very important that you do a hazard evaluation that looks at what the normal conditions and the abnormal and upset conditions are that could occur within the facility. Also looks at the combustion characteristics, that is it possible to ignite the dust that's going to be found in the various vessels within the biomass facility under these upset or abnormal conditions. What type of ignition control has been employed at the facility? Do you have spark detection and suppression on conveying ducts and drop chutes where an ignition source could be generated and then transmitted to a different part of the facility where it could create an explosion? Is there proper electrostatic bonding and grounding? We all know that from the previous information that there's a very low ignition energy tolerance for dry wood products, and electrostatic ignition is certainly enough ignition energy to initiate an explosion. So is there proper grounding for the various vessels that you're going to find within this facility? Equipment electrical classification. In areas where you're going to have a propensity for there to be dust on a regular basis, do you have Class 2 Div 1 rating within that area? And do you have the proper NEMA rated electrical equipment so that an electrical fault doesn't cause an ignition and subsequent explosion? Control of friction and impact sparks. Are you looking at bearing temperature monitors or something that's going to tell you when you have a hot spot that could lead to ignition? Do you have proper housekeeping? If you were to have a deflagration within the facility in a process vessel, and that deflagration were to be released into the room, and the shock wave traveling faster than the fireball, and that shock wave could liberate any dust that's on horizontal surfaces and cause the room to become a secondary enclosure and a secondary explosion. Do you keep your dust loading within these horizontal surfaces down so you don't have this risk? Do you have a housekeeping process within the facility so that you're cleaning on a regular basis so that you do not maintain these deposits of dust? Has the operator's been trained to understand what the risks are of combustible dust explosion, to make sure that they're not doing hot work without vessels that are being cleaned out? Just as a side note, I actually was at an explosion, the aftermath of an explosion in which a dust collector had been shut down. Hot work was being done on the dust collector, but the pulse jets had not been turned off. And when the dust that was being liberated from the pulse jets inside the dust collector reached that hot spot, it caused an explosion with 2 fatalities. So proper training for the operators and for the maintenance people is an absolute vital part of an overall explosion protection strategy. Having proper explosion protection on the vessels that are at risk, and having explosion isolation on those vessels to make sure that you're not running the risk that flame can travel from one vessel to another and cause these devastating secondary explosions. That is the conclusion of my presentation. I will turn this back over to Anna.
Thank you, Dave. That rounded out the panel really nicely. We have time for just a few questions. If you have one, definitely please submit it now. Our speakers will follow up with unanswered questions sometime after the webinar. I'll just jump right into our first question, guys. It's from Walter Miller. And Walter asks, within a building, what depth of a biomass pile can be protected from fire by automatic sprinklers located at the roof?
Well, this is Martin with Jensen Hughes. Because I'm actually a fire protection engineer with fire protection experience, I can answer that question. I'm not sure if I heard it correctly, but it sounded like the question was how much accumulation of a dust layer on surfaces in the building can a fire involving that material be controlled by sprinkler protection. And actually, it's not the dust layer that is an issue, it's the overall combustible loading in that facility. So normally you would not consider dust layers as a factor in designing fire protection or sprinkler systems. There are many more hazards in industrial occupancies that pose much more significant fire hazards for dust layers than dust layers.
Great, thanks, Martin. The next one is actually for you specifically. It says, Martin, is a process of blown-in cellulose insulation on site also an explosion hazard?
The process of blowing insulation on silos I would not say that constitutes an explosion hazard, because the result, if it did become involved, if it was ignited, then it would probably be at worst a flash fire, mostly because the material is limited in the quantities. The insulation, if it's sprayed as a mist, the finer the mist, the more readily ignitable the material is. But that is not usually identified as a building explosion hazard, more so a fire hazard than any other kind.
Got it. Thanks. Okay, our next question's from Scott Berg, and he asks, why is the percentage of dust collector explosions far greater in the U.S. as compared to European countries? Does Europe have higher standards or better practices than the U.S., or is there a lack of reporting?
This is Dave Grandal. I'll try to address that one. I believe that in Europe, you're going to find that the requirements for explosion protection are much more stiff. In the U.S., NFPA is a set of codes and standards that are often enacted by law by various states and jurisdictions. However, not all fire enforcement agencies are familiar with really all of the explosion risks that can happen in various vessels in the U.S. In Europe, it's basically required. If you're going to provide a dust collector, you're going to have explosion protection on it. They seem to be a bit farther ahead in Europe than we are here in the U.S. at mitigating explosions within not just dust collectors, but within other styles of process vessels. We're catching up. NFPA 652 is going to go a long way towards helping us get to that point where we can see a reduction in these events, but we're just not there yet.
All right, thank you. Here's the next question from Bruce Smith. He asks, with a flap valve between two equipment pieces, it looks like it will only protect both vessels if the incident occurs in the vessel that's normally downstream relative to the check direction. What happens if the incident is in the other vessel? Can it ever protect both vessels?
No, and Bruce, no, actually, it will not. The flap will only work in one direction. I've not seen any flap-style valves that are bidirectional. There are other types of flow-activated isolation valves that can be used in some applications that are bidirectional. However, those have some very low dust loading limitations. I'm trying to remember off the top of my head, I believe 50 grams per cubic meter of airflow is the maximum for those styles. When we have an application in which we're trying to stop a deflagration from traveling from either vessel, then generally we would either use a chemical barrier or a high-speed isolation valve.
All right. This is going to be our final question just because we're about 5 minutes over time. The question is from Bob White, and he's wondering what qualifications are required to perform a DHA.
This is Martin again. I think I might be the best panelist to answer that question. The NFPA technical committees have been very deliberate in not specifically requiring that or outlining the qualifications of someone who performs a DHA. The complexity of operations is across industry varies, and with particularly biomass handling, wood handling processes, they can be complex and it cannot be straightforward. So it's important, as with anything that you would look for technical people to design, you would want to have a professional engineer, preferably someone who is certified and has is able to demonstrate that they have a long track record of experience in hazard identification methodologies, who are specifically familiar with the types of tests that can be performed to characterize material hazards, and can also offer operators practicable recommendations that can be implemented at their facilities.
Thank you, Martin. That's about all the time we have for questions. Again, we'll move forward unanswered questions along to our panelists so they can reach out to you. A free recording will be available on biomassmagazine.com within a few days. And with that, I'd like to again thank today's sponsor, IEP Technologies. Those of you who tuned in today are eligible for an exclusive 10% discount to the International Biomass Conference and Expo being held April 16th, 18th in Atlanta with code IBCESAVE10. And finally, be sure to check out these upcoming events that you might be interested in. Thanks again to our speakers, sponsor, and attendees, and we'll watch for a replay at biomassmagazine.com. Have a great day.